Okay.
As you can see,
So here's a video I saw today. And
coefficients return to the
you can see a different
returns to its
version
original
of juggling roots
This means
going
that
on
the
here.
set
You see how these are moving?
Yeah,
five
they're
solutions
kind of like
at
going
the end
in
of the
circles
loop
and then coming
must
back to
return
where
to
they
the
were
original
before.
set.
Yeah.
However, as you can see here,
Now what's
this
going
is a
on?
real
You're right. These ones are all coming back to where they were before. What's happening over here?
These,
Well, there's three of them that are just
imaginary
staying where they are,
solutions
and then
coefficients
x3
really
and
represent,
x4 are
solutions
switching
to this
spots
equation.
each time.
You can
Okay.
see that. at
So
the
if
end
I
of
made
the loop,
3D
when
prints
the
of this one
each
moving through
particular
time, what would it look
solution
like?
should follow it
Well, you'd like
continuously
some
doesn't
spirals.
necessarily
You have some
returns to
spirals
its
and you have some
original
straight
location.
lines, it looks
What
like.
you
I'd have some spirals and straight lines. And what would I have over
You'd
here?
have two spirals that sort of twist around each other, and then two straight lines.
Okay. Very good. Very good. So what this video, and we're not going to watch
This is what we're going to use.
the whole thing by any stretch of the imagination. It's almost half an hour long. This is explaining how these juggling roots allow you to show that fifth degree polynomials do not have a general formula to be solved.
Cool.
Yeah, so
Always gives one of these.
it's not just really cool pictures that we're seeing
Expression would give it.
when we study this. We're actually seeing some really, really deep math and something that I've been hoping I could figure out how to explain to kids for a long time. So later in this part of the video, he's showing a linear equation with only one root. That root always has to go back to itself when you do these loops. But with a fifth degree polynomial, the roots don't always go back to themselves when they do the loops.
Some time to repeat.
It takes some time to repeat. That's right. So now here's a third degree one, and watch what happens to the roots. What are the roots doing on the third degree one?
So they're just going to the 3 points of a triangle and will repeat every third time.
Yeah, and certainly in this example, it will repeat every third time. That might not always happen, that it repeats every third time, and it might not always be the case that they loop around in a kind of a circular pattern like that. But it's going to turn out that when you do the loops, the third degree ones always do come back to where they started, eventually. But the fifth degree ones don't.
Always.
Not always. And the different ways that the 5 roots can loop around, and we saw 2 ways. One where there was 1 in the middle and the 4 rotating around the outside. One where there was 2 in the middle switching places and 3 looping around the outside. The different ways that those roots move around produce a different environment for fifth degree polynomials, fifth degree and higher, and it means you can't solve them in general. Yeah, it's actually really amazing. And you know, it's fun because for me, I've always wanted to figure out a way to try to explain this to kids. I'm trying to get to one more kind of neat picture. Actually, maybe the pictures are only at the beginning. Well, this is actually kind of neat at the end. So, for a third degree polynomial, where you have 1, 2, and 3 in the roots, it comes after 3 times when you follow the procedure described in this video. In a fourth degree polynomial, everything will be back to where it started after 4 times.
Okay.
But a fifth degree polynomial, the roots can jump around in 120 different ways. The first time, 60 the second time, 60 the third time, 60 the fourth time, 60 the fifth time.
It just keeps going like that.
Yeah, see how the roots in the fourth degree go 24 times they can jump around, to 12, to 4, to 1. The third degree one goes 6 to 3 to 1. The second degree one goes 2 to 1. But the fifth degree never stops jumping around.
It's cool.
And the basis of it is exactly what we've been looking at with these juggling roots. It's really cool.
Yeah.
I've always wanted to be able to show this to kids, and now you know that a second degree polynomial can be solved by what?
Secondary polynomial can be solved in 6 rotations. Well, no, 3. Sorry. Or 3, like, don't know what you'd call it.
How do you solve a second degree polynomial?
So a second degree polynomial, it has two solutions.
Right, and how do you solve it?
Well, you just use the quadratic formula.
Right. A second degree polynomial is solved using the quadratic formula. A third degree polynomial and fourth degree polynomial have similar formulas. So they're just much more complicated. But a fifth degree polynomial has no general formula for how to
What about
solve.
like higher polynomials?
It's actually a good question. Maybe a sixth degree one has a formula.
Well, I mean, it gets more complicated. It seems to get like more complicated as you go on, so they might not be able to be solved.
Yeah, and not only that, a sixth degree polynomial is a fifth degree one times a first degree one. So if you could solve a sixth degree polynomial, then you'd be able to solve a fifth degree one.
So it's not.
So anything
likely.
beyond a fifth degree polynomial you can't solve.
Well, you can't write down a
You
general
can't
formula
generally
that
solve
solves all of
It's like
them.
only one.
Like the quadratic formula solves all quadratic equations. The Cardano's formula solves third degrees, and there's one for fourth degree as well. But they're very complicated, and no one remembers them. But fifth degree can't be solved.
No formula.
All right, good work, guys.